right, good afternoon everyone, and welcome back to Algorithms and Data Structures. Now, before we begin here, quick check. Can you hear me? Can you see me? Does it seem to be all working? Yes and yes. All right, good. Okay, people can hear and see me. Excellent. So, like I said, welcome back to Algorithms and Data Structures. Week 7, that should read. Okay, great. I thought I updated the cover of the slide, but I updated it incorrectly. Week 7, the lecture. And today we get to talk about topological orderings and shortest path algorithms. I say algorithms because we will be studying two different algorithms to find the shortest path in a graph. But before we do all that, quick recap. So last week we introduced graphs, and we took a look at different graph traversals. We took a look at breadth first search and depth first search, two ways of answering the question, is there a way to get from A to B? Now today, as I mentioned, we'll take a look at topological orderings and shortest paths. And in the rest of this week, we'll take a look at minimum spanning trees, and next week is all about P versus NP. And then there's two more exams somewhere in the future. Unfortunately, I have no updates for you on that yet. You may have seen on the official TU Delft Corona page that the TU Delft is requesting you to still register for your exams. I'm not sure if you still can for hours, because it's exactly 2 weeks from now, or scheduled to be exactly 2 weeks from now. So I think registration may have closed, but still try to follow these orders as much as you can. As soon as I know something one way or the other, I will of course let you know, but I am still awaiting official TU Delft policy on this before I can communicate anything to you. That being said, you have done 2 other exams already, and I have finished grading them. I'm not going to discuss the results here on stream. I think this is a bit too public of a setting to do so. But I have published the grades on Brightspace, and if you have any questions about the way you've been graded, please send me an email at the course email address, and I'll take a look as quickly as I can. Did all of you see that the grades were available? And perhaps more importantly, did you get an email from noreply@tudelft.nl with feedback on your written exam? Because it's the first time I tried to send this email from home rather than from the office, so I don't know if it worked. Okay, people are confirming they saw the grades. Let's see about the email. Or is that what you meant, Sophia? Cisco didn't get an email. Okay. Did not get an email. All right, then I need to take another look at that. I'll take a look immediately after stream and try to figure out what went wrong there. You should get an email very soon that contains a scan of your written exam as well as some feedback on how that has been graded. I'll look into it after stream. Thanks for letting me know. I'll ask again tomorrow morning, then see if you got it by then. All right. Do you have any other questions before we get started here today? I don't see any popping up. Then I suggest we just get started. And if you have any questions anyway, I'll try to answer them later. All right, so last week we talked about graphs. Graphs that were just these lines and circles connected together in some way. And we had different versions of these graphs. We had undirected versions, directed versions, weighted versions, unweighted versions. These circles we called vertices or nodes, and these edges or these lines were called edges. Great, and we saw a whole bunch more naming related to graphs. And we also identified 4 questions that someone like the Dutch railway network might be asking. For example, if I am currently in Delft, what other cities can I reach? Well, this question we answered last week, right? We can find out what other cities we can reach by using a BFS or DFS traversal. But then you might be interested to know, okay, so great, from Delft I can reach Groningen, but how do I get there the quickest? That's the answer, or that's the question we will be answering today. Tomorrow we will have another, regular lecture instead of a tutorial. There might be one small programming assignment, but it's mostly going to be lecture style. That was already planned for this week, by the way, so that's not because of the whole current situation, but this week was planned to have 2 lectures, 1 tutorial. It's just that I couldn't get Chip today, so we would, or tomorrow, so we would have been in Pulse, but my lecture plan was to have 2 lectures. Anyway, tomorrow we will look at minimum spanning trees to answer questions like how can I connect a new station to the network? And next week we will talk about quickly touring the entire country, and I'll show you that we believe that problem to be very difficult. Okay, so let's take a look at these questions of today. So one of the questions is the shortest path question, but before we do, there is one more ordering, traversal isn't quite the right word, as we'll see in a moment, but one more ordering I want to take a look at. We call them topological orderings. So what's a topological ordering? Well, consider that you have a bunch of things that you need to do that depend on each other. Now I'm looking for an order in which I can do all of these jobs, all of these things, so that all of the dependencies are met. And you may remember that this was a use case of a pre-order traversal in a binary tree. Pre-order? Yeah, I think so. Yes. First do the root and then do both of its children. However, of course, it doesn't have to be the case that all of these dependencies form a nice tree-like structure. They could also form a graph instead of a tree, because one job might have multiple dependencies coming in and might indeed be a dependency for multiple other jobs. So in that case, we need not a tree but a graph, and we need a special traversal of this graph. Now, consider as an example that I need to create an exam, then I have to proofread the exam and I need to print the exam, I need to make an answer sheet and print the answer sheet, and finally I need to bring everything to the exam location. Right? A simple set of 6 tasks. Now, what I'd like you to do, please, is turn this into a graph where the tasks become vertices, dependencies become edges, and then I want you to find me an order in which I can do these tasks. I'll give you, let's say, 1.5 minutes to quickly make a drawing while I get my tablet set up, and then we'll take a look together. There we go. See you in a bit. Okay, so let me move this out of the way and open up my tablet here. Let's see, where did it go? Here it is. All right, and let me see if we can quickly draw this graph. So we have the task, create exam, I'll just call it C. Then I need to have the exam proofread, exam proofreading. I need to have the exam printed. I need to make an answer sheet. I need to print the answer sheet. And I need to bring everything to the location. These are the tasks I have. Now let's add the dependencies between them. Well, before we can proofread an exam, I need to make sure I have created it. And before I can print the exam, I want to make sure it's proofread. And before I can bring it to location, I need to make sure it has been printed. Now, similarly here, answer sheets I can only print after I've created them. I can only bring them after I've printed them. And in order to create an answer sheet, I will have to have made the exam, otherwise I don't know how many questions to put on my answer sheet. And here we see that we have an example of one of these dependency graphs, as we call them, that isn't a tree, right? Because C has 2 children, but BEL has 2 parents, if you want to think of it in terms of a tree, which, well, because it has 2 of them, can't really be done, right? And now what we're looking for is an order to complete these tasks in. Well, we will have to start with creating the exam, and now we can choose, right? So for example, we could say 1, 2, 3, 4, 5, 6. But we could also pick 1, 2, 3, 4, 5, 6. Right? So long as we have an order in which all of the dependencies are done before a job itself, it's going to be fine. Does this make sense? Are there questions about this model or the way I've found one of these orderings in which I can do the tasks? I'm going to give it 5 more seconds on my end to see if a question pops up. Good question. What if we want to do 2 tasks at the same time, asks Urg. Well, that's not something that this model supports, right? So in this model, we have what we call sequential tasks. We do them one after another. If we want to add parallelization, the problems becomes a whole lot more interesting, but also unfortunately outside of the scope of this course. It's a good point, but unfortunately not something that we can solve with the models we will discuss. Okay, I see no other questions, so let me transition back to the slides and let's take a look at what this all means. So we've seen an example now of one of these orderings. Well, and one of these orderings that we just created, we call a topological ordering. It's an ordering of all the vertices, where basically we give the vertices a number, as I just did, right? In such a way that for every edge, it goes from a smaller number to a larger number in our numbering of the vertices. And now there's a nice claim. I claim that a graph has a topological ordering if and only if it is a DAG, directed acyclic graph. Okay, that's a term we saw last week, right? A graph that has, where every edge has a direction. It's acyclic, meaning there's no cycles in the graph, and well, G, it's a graph. Okay, let's see. Let's prove this. Well, it's an if and only if, so we need to go two ways. First, suppose it has a topological ordering. What does that mean? Well, it means that we have this ordering, this labeling of the vertices 1 to n. Now we'll use a proof by contradiction to show that this graph must then be a DAG. So assume there is a cycle. Well, that means that starting from some vertex, let's call it x, we have an edge to Vy, and then on and on and on and on. And then at some point, Vw, we go back to Vx. But due to the way our topological ordering is constructed, we know that x must be smaller than y, because there's an edge from x to y. Y must be smaller than whatever comes after that. So y must be smaller than w. But now w must be smaller than x, because there was an edge from w to x. And that's impossible, right? X cannot be both smaller and larger than itself. So, x cannot be smaller than itself, rather. So the first part, if it has a topological ordering, it must be a directed acyclic graph. We've shown that. Now the other part, if it's a directed acyclic graph, it must have a topological ordering. That's going to be a bit trickier because now I need to, given a direct acyclic graph, I need to construct a topological ordering. So let's first think of an algorithm that can do this for us. What could we do? Well, it starts with one basic observation. If it's acyclic, so if there's no cycles in the graph, there must be a vertex somewhere in the graph that has no incoming edges. Why is that? Why must there be at least one vertex without any incoming edges if the graph is acyclic? Let's see if one of you can tell me. Otherwise there is a cycle, says Cisco. Yeah, that's definitely true. I was hoping for a little bit more than that, but you have to start somewhere. Yeah, also true, Gideon. So again, let's use a proof by contradiction, right? Yeah, so Sophie also says you need to have an initial vertex, and Urg also, because if it is acyclic, there is one vertex that has to be the beginning. Yeah, the beginning of a graph is a little bit vague, perhaps, but imagine that it is acyclic, but that also every vertex has an incoming edge. Then what can I do? Well, given a random vertex, I can traverse backwards over its incoming edge, so I end up somewhere else. And now again, this one must have an incoming edge, so I traverse backwards over that. And if I do that v times, where v is the number of vertices, then I must have created a cycle. And every time, because every vertex has an incoming edge, I must be able to go back. Well, since that's impossible because the graph is acyclic, there must be at least one vertex without any incoming edges. Okay. And now indeed, so as you all mentioned, right, we have to start somewhere, we need to have an initial vertex. Well, exactly, so this is going to be our initial vertex. We can start with that one vertex that does not have incoming edges. We put that in our topological ordering, and now we remove all its outgoing edges. Which means that now we have created another vertex without incoming edges. So we can repeat this procedure. If we put that into pseudocode, we get something like this. A topological ordering for a graph G. We need to keep track of the ordering that we're going to construct, and we need to keep track of a queue of vertices we can now take. Well, as is correctly pointing out, there might be more than one of these vertices, right? There could be multiple vertices without any incoming edges. So we take all of the vertices without incoming edges and we put them in our queue. Now, so long as there's something in the queue, take the first vertex from the queue, put it in our topological ordering, and remove all of its outgoing edges. if after removing such an edge, the vertex that this edge was going to has no incoming edges left, if its in degree is 0, then we can now add this vertex to the back of our queue, this way for you. No, that would be the front, this way for you. And we move on to the next one. So that's just a bunch of ends in the pseudocode here. Right, so first take all of the vertices with 0 incoming edges, put them in a queue, start handling them one by one. And every time we take one of these things out of the queue, take a look, okay, where are your edges going? Good, remove those. If we now find a vertex that has no incoming edges left, then we can take this vertex and add it to the end of our queue, so that after we've had all the ones with 0, we can now safely take this one. Now, what does the runtime of this algorithm look like? Well, if we implement it efficiently, then finding the first vertex or the first vertices will require going over all of the vertices once, so that's theta v. Then we consider every vertex at most once, right? Every vertex is removed from the queue at most once, so that's also theta v. And we consider all of the edges once, and in fact we remove all of the edges from our graph once. Well, in the map-based implementation that we saw last week, we can do this in theta one time. So removing every edge, that's theta e. So all in all, it's v plus e. Right? If there's way more edges, that one will be the dominant factor. If there's way more vertices, that one will be the dominant factor. But both play a part. Are there questions about the runtime or the way this algorithm works? Browhead's asking us, I don't know why it's theta e. So that's a good question, and I'll get to your question in a second, Okomon. So Browhead, let's start with yours. Why is it theta e? Well, for every vertex, we're going over all of its outgoing edges. So initially you might think, okay, so then it's v times e, maybe, right? For every vertex, every edge. But what we're actually doing is, for every vertex, we consider only its edges, its subset of edges. And that means that every edge is going to be inspected exactly once. Namely, when its outgoing vertex is removed from the queue. And so every edge is removed from our graph exactly once, and that gives us a theta e term. Does that make sense, Browhead? In the meantime, let me answer Okomon's question. So when you have theta v plus e, can't you also say theta max v of e, v and e? Yes, you can. So this is not something I've proven in the course, but you can try and do this yourself if you like. But theta a plus b is the same as theta max a comma b for any a and b. Any a and b. Yeah, pretty sure that works. Well, any positive at least. But even with negative, well, negative in a big O is something I've never done. Yeah, pretty sure it would work for any. So if you want to, feel free to prove it for yourself, Okomon. But yes, in this case, you're absolutely right. Theta v plus e is the same as theta max v comma e. Does that make sense, Okomon? Excellent. Good. Okay. Then, we've seen the code for this. Now there's one more remark about this. So last week we discussed breadth first search and depth first search, DFS and BFS. And they give us an ordering of the nodes. And now we've seen topological ordering, which also gives us an ordering of the nodes. But is there any difference between how these two work, other than, of course, the order in which we return the nodes, right? So BFS, DFS give a different ordering than the topological ordering gives. There's different constraints on them. But is there another difference between these two? Or these three, rather? Any ideas? I'm gonna give you a couple more seconds, otherwise I'm gonna give it away. Okay, it's a nice answer, Shumpum. Not a way I'd thought about it before, but Shumpum says topological order allows for teleportation. It's very nice. Yeah, there doesn't have to be an edge directly between two consecutive vertices. Now with DFS, but also BFS, maybe we could also see teleportation in some cases. But with topological ordering, it's a little bit more common, I would say. That's definitely true. But it's not quite the answer I had in mind. The answer I had in mind is that DFS and BFS can be executed only starting in a node. And they will give you a different result when you start in a different node. Furthermore, they might not give you all of the vertices in the graph. So indeed, as Jan is pointing out, a topological ordering will give us all of the vertices in the graph, and it's a property of a graph. It doesn't depend on one specific vertex, right? So a graph has one or more topological orderings. Well, a DAG has one or more topological orderings, whereas from a vertex, we can do a DFS or a BFS traversal. And this might, like I said, not give us all of the vertices. Consider, for example, a simple graph that has two vertices that are not connected. So there are no edges in the graph, it's just two vertices. A BFS from this vertex will only give this vertex, whereas a topological ordering of this graph will give, well, one of two orderings of these vertices. Right, so these are important differences to recognize. BFS, DFS require a starting vertex, and their ordering depends on which vertex you choose. Topological ordering is a graph property that does not depend on a specific vertex. Okay. That was all related to topological orderings. Now let's get to this second question of DNS that we will be solving today. And let's talk about Dijkstra's algorithm, something many of you will probably have heard of before. So Dijkstra, Edgar Wiebe Dijkstra, is the inventor of this, a Dutchman, which makes us all very proud, of course. He published this algorithm many, many years ago now, in 1959, and he claims to have invented it 3 years before that time, when he was having a cup of coffee on a shopping spree together with his then fiancée. He was thinking, okay, what's the quickest way for me, to get out of here? I don't know if that's the right way of putting it, but he was thinking about this, and in just 20 minutes with a pen and a piece of paper, he wrote down what is now one of the most famous shortest path algorithms we have, namely Dijkstra's algorithm. So how does Dijkstra's algorithm work? Well, let's take a look at that. First, let's formally define our problem. Given a weighted, potentially directed graph, we have the question, what is the shortest path from S to T? So from some vertex to some other vertex, where we define the length of this path as the sum of the weights along its edges. Right, so if I have two nodes with with an edge of weight 8 in between, then and this is everything in my graph, two vertices, one edge, then the weight of the shortest path would be 8. And Dijkstra's algorithm can help us find this shortest path. Now, let's build our algorithm. There's one important criterion to mention here. In Dijkstra's algorithm, we assume all weights to be non-negative. They can be 0, that's fine, but they cannot be negative. Why is that? Well, consider I have a cycle, and the weight of this cycle is negative, meaning when I sum all the edges together in this cycle, I get a negative number. Then I can get an arbitrarily small distance from S to somewhere else by including this cycle many, many times. Right? If you want the shortest path with weight minus 100 or smaller than minus 100, that's fine. I'll include the negative cycle sufficiently many times before going on to ensure that I get to the minus 100. So, Dijkstra's algorithm only works when weights are non-negative. Fortunately, in many shortest path applications, the weights are non-negative because they usually represent time. So until time travel is invented, Dijkstra is safe. Okay, so weights have to be non-negative. What else? Well, we start in some vertex S, and now we take a look at the closest neighbor to S. What do we know? Well, the closest neighbor of S cannot possibly be reached in a faster way than me going there directly. Why is that? Well, going via any other neighbor must take at least as much time as going there directly, and then I still need to do something else to actually get there. Right? So for example, in this case, going from S to D already takes more time than going from S to F directly. And even if it were the same amount of time, I would need something that is at least 0 to still get from D to F. So the neighbor from my start node, that one I cannot reach in a shorter time. And this idea is what the algorithm is based on. Because now I have, now again, I look for the closest node reachable from S. And if we take a look at this little cloud that we usually call it, from S and F, then I can reach B in 9, I can reach D in 4, and I can reach T in 3 plus 8 is 11, right? From my SF cloud. And so 4 is the smallest one, this is D, so again, there is no way that I can reach D in a shorter way than this. And now the next one, I have this little cloud of S, D, and F. I can get to B in 9, I can get to C in 6, and I can get to T in 11 still, via F. So this path can be via an already explored neighbor. C is the next one that we add. Let's see. There's 2 questions asked. Gideon, if you took D as your start, going from D to T directly would take longer than going via C. I agree. So if we take D as our start, then going there directly would take longer. But again, we first consider the closest neighbor. That would be C. Now we consider the closest one from this little cloud of points. So we could go to T in 8, we could go to T in 3, or we could go to F in 3. Right? So in that way, every time we take a look at the neighbors of our cloud instead of the neighbors of one point exactly. And we always take the closest neighbor of this little cloud. Good. That seems to have helped. Okay. And we repeat this procedure until T is the closest one we can get to. Now, let's put that into code. What's that going to look like? Well, bear with me for a second here. First of all, let's say every vertex is very, very far away, right? It's infinity far away. Now, that's quite a bit. Then we have our start vertex. And our start vertex, well, that's where we are now. So that is not away at all. It's at a distance of 0. And now I'm going to repeatedly take the vertex that is closest. Right? To start with, that's going to be my start vertex, because it's at distance 0 and all the others are at distance infinity. Now, if this is the vertex I'm looking for, great, I'm done. Because what Dijkstra ensures us is that every time we take the closest node, there is no way of ever finding a route that is shorter to that node. If it's not, and if the distance is still infinity, right, so it's not our target, but the thing I got out has a distance of infinity, then there's nothing else for me to explore. I haven't found a better way to get to this node. It's still the closest one, which means that there's no way for me to get to T. And now we get into the meat of it. So I have taken out the vertex that's closest. Now I'm going to consider all of the edges leaving that node. And I'm going to check, do they get me a shorter distance to the vertex they connect to? So for example, if this is my start vertex and this is a vertex F, which currently has distance infinity because I've only just started, and there's an edge between them of weight 4, then I'm going to check, okay, 4 plus 0, that's what it's, or 0 rather, plus 4, right? Start vertex is at distance 0, the weight of the edge is 4. 4 is smaller than infinity, so I should update this distance to be 4. And so I update the distance of all my neighbors. Now, I repeat, I take the closest vertex, I take the closest neighbor. Well, if this is not the thing I'm looking for, and it's also not infinity, then I'm going to take a look at all of its edges, and I'm going to check, is there a shorter path through this vertex? So, this distance of 4 to get here, plus whatever distance on these edges, will that get me a shorter path to where these edges point? If so, great, update the distance of these neighbors. I can imagine that might be quite a bit to take in. So are there any questions about this already before we start applying it to a graph? I see no questions at the moment. Let's give it 5 more seconds. Okay, then let's apply it to a graph. So here's a graph, and I would like you please to find me the shortest path from A to I. Now, you can try to do this by hand, and because the graph is relatively small, you'll probably succeed. But I recommend you try and do it using Dijkstra's algorithm to get a bit of a feeling for how that algorithm would solve this problem. So here's a nice graph. What is the length of the shortest path? Our code for today is QLT, and Feedback Fruits is happy to hear your answer. I will give you 2 minutes to solve this one, and then we'll take a look together. Okay, let's see what you think while I also get the tablet set up again. There we go. Okay. An overwhelming majority for 12. Excellent. Let's see if we can verify that. So what we're going to do here is apply Dijkstra's algorithm starting from A, right? We want it to go from A to I. Okay, so we're going to have here our little table with all of the distances. A, B, C, D, E, F, G, H, and I. And for starters, all but our starting vertex are gonna have a distance of infinity. Oh, there's also a node J. Oh, and there's no G. What did I do creating this? This should be a K. All right. Hang on. There's also no E. Because E and for edges and G for graph might get confusing. Right. So once more, F, H, I, J, K. Okay. Let's figure this out. So first things first, we take a look at all of the outgoing edges of A. Let me actually move this back to the code. That might help you in seeing exactly what I'm doing. So we first take a look at all of the outgoing edges of A. Well, that means we update several of these. We're going to update B to now be 9. We're going to update D to now be 4. And we're going to update J. This is horribly constructed, but something like this. To now be 12. Now we take the closest one, right? So we've done this one. The closest one now is D. So we take D. And now we again see, do I need to update any of its neighbors? Well, to C, I have now found the path of 4 plus 8. So the distance to D plus our edge 8. So that's 12. That is an improvement over infinity. So C now has a distance of 12. F, also an improvement over infinity. 4 plus 8 equals 12. And J, 4 plus 3 is an improvement over 12. So this 12 becomes 4 plus 3 is 7. So far so good, because then I'm going to speed up a tiny bit for the next ones. Closest one is now J with 7. So we take a look. It has only one neighbor, F, which we can now reach with 9. 9 is an improvement over 12. So we update the distance to F to now be 9. Next shortest one. Well, we can pick, right? B and F both have shortest, both have 9. So let's do B next. That gives us one update, namely to C, which can now be reached in 9 plus 2 is 11. Then let's take a look at F, which was the next closest one. F gives us an update on K and H. K can now be reached in less than infinity, and H as well, because H can be reached in the distance to f plus 2, so that's 11, and k can be reached in the distance to f plus 1, so that's 10. Closest one, k. That gives us a path of distance to k plus 3 is 13 to h. That's not better than 11, so we don't update it. Next closest one, c, gives us a distance to c is 11 plus 1 is 12 to f. That's not smaller than 9, so we don't update it. Next smallest one is h. So we update the one to I. Oh, I forgot to copy the weight here. What was the weight? 1. So we update our distance to I to become 12. And finally, we take I out of the queue, and that means we are done. And our final answer is 12, as many of you also said. All right, if there are any questions about how I just solved this problem, I will be happy to answer them during the break. For the rest of you, I'll see you back after the break for our intermezzo, as well as the second half of this lecture. See you in a bit. do this. All right. So, welcome back, everyone. For those of you that stuck around during the break and that I had a bit of a chat with about how you're dealing with the current situation, how other courses are doing it, thanks for the feedback. I very much appreciate it. Good to tune in a little bit and see how you're dealing with this, whether I can do other things or... but it turns out that other courses are using different systems as well. So via Blackboard, I didn't know we still had a license for Blackboard, but cool that that still exists. All right, cool, thanks. Yes, just after the break, which means it's time for today's intermezzo. Now, a few weeks ago, when we talked about queues, I told you a little bit about the internet. And I told you that the internet is nothing more than a whole bunch of wires, routers, and algorithms. And back then I told you that, well, when I sent a message, right, it was just a whole bunch of queues that this thing would go through. First in my operating system, then in my router, then more routers, then the operating system of the server, and then the server would handle it and send it back through all of these queues. But step 3 says it passes through another bunch of routers. Which routers though? Right? How do I actually get my message from my computer to Google's servers? Or in the case of Twitch right now, right? How do you get a message from your PC to the Twitch server to request in exchange a bit of video? Well, for that, we need to determine some orders, some route of routers. And there's two different protocols that the internet uses for this. So on the one hand, there's distance vector routing, and on the other hand, there's link state routing. Let me tell you briefly about both. So distance vector is just every so often, a router goes to all of its neighbors, so the one that directly has a cable into them, and it asks, hey, what other routers can you reach, and how long does it take you to do so? And based on this, it updates its own information, and every time it gets a packet, all it needs to see is, okay, which neighbor claims to have the best route to this destination? That one, great, I'll send it there. That's distance vector. You only ask your neighbors, what can you reach and how long does it take you? And based on that, you make your decision. The alternative is link state routing. This means that every router tells every other router, so not just neighbors, but everything in the network, about the edges it has and the time it takes for a message to travel along these edges, along these wires. And a router then uses Dijkstra to compute the shortest path to a destination. Now, there's advantages and disadvantages for both, and both have one very big disadvantage that's different for both of them. In distance vector routing, I ask my neighbor, what's the shortest route you have to place A? And it might say, well, my shortest route is length 18. But that might rely on the fact that that router is thinking, yes, to get to destination A, I'll just send it to you first, and then you have a route of length 17 to send it somewhere else. So the shortest path that your neighbor thinks to have may be a path through you. And this can result in many problems when one of the routers drops out. Right? In the internet with millions of machines turn off and on all the time. And if one of these suddenly drops out, we get what we call the count to infinity problem, where two routers next to each other keep thinking the other one still has a path available, and they update the cost as we go until they reach some point, until they reach infinity, or at least the largest number a router can handle. The problem with link state routing, you may have already guessed, right? The internet is huge. It's sometimes described as the largest man-made invention. And there is millions and millions of machines connected to this thing. So keeping track of this entire network requires a lot of memory, and then executing Dijkstra on it requires a lot of time. So that's not great either. So what do we do? Well, we use them in different settings. So distance vector is usually used in, let's say, some sort of overarching layer, right? I have a subnetwork here, and I have a subnetwork there, and a subnetwork there. I need to get from this subnetwork to another subnetwork. Which other subnetwork do I use as in-between points? So it uses a high-level routing protocol. Whereas link state can be used within one of these subnetworks that has a relatively small number of nodes to find the best route in there. That's one example, right? So distance vector and link state are two shortest path algorithms. Only link state, I'd argue, really is guaranteed to find you the shortest path because it uses Dijkstra. Both of these are used in the internet to send messages from A to B. Okay, that's shortest paths in the internet. Let's get back to shortest path in general in graphs. And let's take another close look at this Dijkstra's algorithm. Just before the break, we studied its code and we have tried and do it for one example. And on this example, it indeed found the shortest path of length 12. Now I claim that Dijkstra's algorithm, I see the apostrophe S is missing here, that Dijkstra's algorithm always finds me the shortest path from S to T. Let's prove that. And can we prove this? Yes, of course we can. And we can do so using induction. So what's that going to look like? Well, let's get a bit of nomenclature out of the way first. I already informally used it, right? We have this cloud of vertices that we've already considered. To start with, it's just the start node, and then the closest neighbor gets added, and then the closest neighbor to this cloud gets added, and so on and so forth. So every next vertex we consider is a vertex that's not yet in this cloud, but is now the closest to S. That's the way we define this cloud. Then, what I'm claiming is the following. For every vertex in the cloud, the distance I currently have recorded is the smallest distance to get there. Because as soon as I add it to my cloud, I say there is no shorter path to get there. So d of v will no longer be updated, and d of v is the smallest distance. For all of the vertices not in my cloud, the distance currently in the distance matrix, or the distance table, whatever you want to call it, is the smallest distance that uses only nodes inside the cloud, except for the final edge, right? So the final edge is the one that brings us from inside my cloud to this new node u that is not yet in the cloud. So d of u contains the smallest distance to get there through only vertices inside my cloud. Or infinity, if I cannot reach it one edge from my cloud. Now that might sound, I don't know if this sounds complicated. For computer scientists it might, but I hope that you've seen stuff like this before, so that for you this is a little bit easier to parse. Now then, let's prove that this claim is true. So first, consider the case where I have only one vertex in my cloud, namely my start node. Well, the algorithm says that the distance to my start node is 0, and all of the neighbors are going to be exactly the weight of the edge to the neighbors. Why? Well, because the weight of this edge must be smaller than infinity, and therefore we update them. So that means that indeed our claim now holds, right? There's only one vertex in our cloud, that's d of s, and d of s contains the smallest distance to get there, namely 0. And for all other vertices that are not in the cloud, either they contain infinity, because I cannot immediately reach them from my cloud, or they contain the smallest distance to get there through only vertices in the cloud, which is to get there directly from S. That's the base case. Then induction step. So first we have an induction hypothesis. I assume the claim holds when I have n-1 vertices in my cloud. Now take the unexplored vertex v with the smallest distance, right? Remember, that's what Dijkstra did. So Dijkstra takes the smallest vertex that we have not yet explored, and we add that to our cloud. Now, this must be the smallest possible distance to v through all of the nodes in our cloud. This I know from my induction hypothesis, because v at that point wasn't in my cloud, so d of v must contain the smallest distance to get there through only vertices in the cloud, through only explored vertices. Now, if there is a path through an unexplored node that is shorter, right? So again, we're going to somewhat use a contradiction here. Let's say there is a path that goes out of my cloud earlier and then gets to this new node V that is shorter. Let W be the first node along that path that is outside of the cloud. Now, what do I know? Well, the distance to W must be larger than the distance to V, because V is the one I chose as being the closest one, right? The smallest distance through our cloud. So that means that going to this W first can never result in a shorter path. And therefore, Dijkstra's algorithm, or therefore this claim also holds when I've added one more vertex, and therefore, by induction, it holds. And thus, Dijkstra provides the optimal solution. Does that make sense, or are there questions about this proof? I've purposefully chosen to give an alternative version of the proof compared to the one that's in the book. So if this one doesn't have you convinced, well, it is from a computer scientist after all and not a mathematician, perhaps the proof in the book can truly convince you. Give it a couple more seconds here to see if any questions pop up. Doesn't look like it, so let us move on. Okay, so we see the code. I've proven to you that it is correct. It gives us the optimal solution. Now let's see what is the runtime of this algorithm. Well, let's go through it step by step. So first thing we do is we create this distance table and we set the distance of infinity for all vertices. Okay, we do something for every vertex, vita v. Then we have a while true loop. Ooh, that's nasty, because if this while true loop never terminates, our runtime is going to be infinite. So let's get back to that later. Then we take the smallest distance, the vertex with the smallest distance. Okay, that would require looping over all the vertices, I guess. So yeah, vita v, probably. Now, just two quick checks, right? Is it the vertex we were looking for? Is the distance infinity? I can do both in constant time. Then I iterate over all of the edges. Okay, over all of the edges that leave a vertex. So that is the degree of that vertex. Yeah, which worst case is vita v, right? Every vertex can have no more than vita v edges leaving it. Namely, one edge to every other vertex. Then I need to update the distance. Okay, can do that in vita one time. So that gets me to a time complexity. Oh wait, there was still that while loop. So the while loop, well, how often do we do this? Well, worst case, I get every vertex out of this queue, or every vertex once, right? There's this cloud which I'm adding stuff to, and I should never consider a vertex that's already been added to the cloud. So worst case, until either T is explored, which requires going through all the vertices, or I cannot find T and I go through all the vertices. So yeah, vita v for this while true loop. Now, unless I'm very much mistaken, that means I have a total of v squared time. V for every, the while loop repeats vita v times, and inside we do vita v work. That's v squared in total. Okay, is that good? Is that bad? Well, I don't know. Let's see if we can make it a little bit better, question mark. Well, what we could do, or what we notice rather, is that this m, right, finding the smallest one takes us vita v time. So perhaps we can do something slightly better there. So could we improve the runtime by using one of these data structures? A double-ended queue, a priority queue, maybe an AVL tree. What could we do, if anything, to improve this? I'll give you a minute or so to figure it out, and Feedback Fruits is happy to hear your answers. All right, let's take a look then. Only 7 people answered. Maybe 5 more seconds to give me some answer if you have one. Looks like we'll have to settle for 10 people today. Which means, perhaps unsurprisingly, that it's very easy to get a very nice spread. A third for C, D, and E, and 1 vote for B. Okay. What do we have? We have a bunch of vertices, and I repeatedly want the smallest vertex. I repeatedly want the smallest vertex. Well, a double-ended queue, I'm afraid, is not going to help us, because that's just going to give us a first-in, first-out order, but I have some sort of weighted order. And that's exactly what a priority queue is used for. Could we also use an AVL tree? Maybe. We would always take the bottom left child. So yes, an AVL tree could also work, but we tend to use a priority queue for this one. So how would that work? Well, if I store the nodes in a priority queue, then to start with, I need to insert all of them. That takes v times log v time. I need to update the distances, and remember our priority queue had this update key operation. Or rather our heaps did, and therefore our priority queues did. And someone asked back then, why can we only do decrease key and not increase key? Well, we could also do increase key, I suppose, but this is the reason why. In Dijkstra, we only need decrease key. So indeed, Gert, we use a priority queue based on a minimum heap that allows us to insert stuff in vlog vtime. It allows us to update these things. Well, worst case, for every edge, we need to update the distance. So that would be e times log vtime. And we need to remove the smallest value, v times. So that's v log v, which gives us a total of v plus e log v time. Is that better? Well, that depends, right? It depends on the size of e. V log v is better than v squared. But e could throw some, root in het eten in Dutch, could spoil this for us. It truly depends on how many edges there are in the graph, which one would be better. That being said, this is the implementation most commonly used. So when we look at the most common Dijkstra implementations, you will most often find them using a priority queue to effectively get or efficiently get the next vertex every time. Okay, so we could do it in v squared by just keeping track of a simple table, a simple array of distances. We can do this thing a little bit better by using a priority queue. Now that's great, that's Dijkstra. But then someone thought, okay, Dijkstra is great. It's also 60 years old. Can we not improve it? And someone did way before they had to think it's 60 years old. So can we improve over Dijkstra? Yes, we can. Consider the following example. I want to find the shortest path from A to B in this graph. Now, you can probably immediately see that there's only one path from A to B, namely a direct edge with a length of 9001. However, what's Dijkstra going to do? Right, so we immediately see the answer, but Dijkstra is first going to explore 9000 other vertices, because V1 is at a distance of only 1, so that's closer. Then V2, because that's at a distance of only 2, and that's closer than the vertex B at the distance 9001. Then vertex 3, and then vertex 4, and then vertex 5, and so on and so forth. And I can make this arbitrarily large, right? By making all of the edges to the left have 0 cost, I can add arbitrarily many vertices to the left and arbitrarily many edges to the left, and Dijkstra will explore all of those before finally giving me the answer that there is only one path from A to B, and it's a path of size or of weight 9001. So to circumvent this worst case Dijkstra, people thought, okay, how about we enhance Dijkstra a little bit? Can we make it a little bit better? And we can by adding what we call a heuristic. Now, a heuristic, according to Wikipedia, is a technique designed for solving a problem more quickly, blah, 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 blah. For our purposes, in the combination with Dijkstra, we use a heuristic to, let's say, take an estimate of how far it would be from our cloud to the target. So basically what we're doing is we're telling Dijkstra, okay, you should take a look, how far is it to this new node, but you should also take an estimated guess how far it would be from that new node to our target. So what could we do for that? Well, for example, when it's a distance thing, we could simply take the Euclidean distance. So that means that when I travel from Haarlem to Delft, that Den Haag is a more likely target to investigate first than Leeuwarden would be. Right? Because the Euclidean distance from Den Haag to Haarlem is smaller than from Leeuwarden to Haarlem, and that makes Den Haag a more attractive target for Dijkstra, or well, for our new algorithm to explore first. In more American-style cities, like New York, the Manhattan's distance might make more sense. Right? In New York, you have all of this grid-like streets, so it's delta x plus delta y. That could be perhaps an estimate. You could take the difference in node ID. Why not? Maybe it will tell us something. So if I've labeled all of my nodes from 1 to n, then why don't I take the difference in ID? It might tell us something about the distance. I don't know. This is based on the assumption that nodes with similar IDs, not ideas, but IDs, are close together. Yeah, that might be true, that might not be true. But if that's true, then perhaps this isn't a terrible heuristic. Or, well, okay, I need to take an estimated guess. I have no idea. I'll just say everything is instantly to the target, right? I just put them all to 0. I have no idea. I could replace the 0 with any constant value. Okay, so these are some heuristics, some estimated or some best effort guesses we could have to determine the distance from our new vertex outside of the cloud to a target. How does this change our algorithm, this notion of including a heuristic? Well, only one line really needs to be changed. I look for the node that's closest, including this idea of my estimate of going from that node to a certain target. Right? So I include a measure of how far the next node would be from my target. Which means that in our previous example with the 9,000 nodes going one way and one hop to the right answer going the other way, if we include a Euclidean distance there, then at some point we will find, okay, we've moved so far left that moving all the way back to the right is going to take us longer. So it would still start exploring to the left, because maybe with a small detour we could still find a faster route. But at some point it would conclude, well, I'm sorry, but going all the way back is going to take too long, and explore the other node. But that sounds a bit worrisome, maybe. Because what if I use a Euclidean distance as a heuristic, but in fact I have a non-Euclidean space? Or if I use this idea of the node IDs, I might be underestimating them by quite a bit, these distances. Well, let's see what happens to the runtime and what happens to optimality. Let's start with the runtime. Well, the runtime doesn't really change. Worst case, we still need to check all the vertices, right? Consider where I actually want to go to this node V9000. I still need to go through all the other ones in between. So worst case, nothing changes. So then why are we doing this? Well, if the heuristic is an oracle, meaning it is always exactly right, then we consider the minimal required number of nodes. This is a nice proven theorem that you can check the proof for in Wikipedia if you don't believe me. And it says if we have a perfect estimate, then we consider the minimal number of nodes. Now, of course, this is a bit, it's a nice property for the algorithm to have, but also a bit unrealistic when it comes to solving actual real-world problems. Because if we have this perfect oracle, the oracle that's always right, then we don't need to use Dijkstra or whatever algorithm we're building now, because we already have an oracle that can tell us the right answer. But our goal is then to get to a heuristic that is as close to this oracle as possible, because then we will get as close as possible to actually considering only the minimal required number of nodes. However, we have bigger problems at our hands. Because if we pick the wrong heuristic, everything might break down. Consider this example. I want to find the shortest path from A to C. I have only one heuristic, one estimate. Namely, my heuristic says that from B to C, that will take us 1,000. All the other heuristics are 0. What is the, I've called it performance ratio, which is a term from complexity theory. It's not entirely apt here, but it does its purpose. So what is the length of the path that we find divided by the length of the optimal path? So if we use our modified version of the algorithm, an algorithm we call A star, so that's just Dijkstra with our heuristic added in, what is the performance ratio for this heuristic? Feedback Fruits is happy to hear it. Okay, let's take a look at what you think. Majority for 2. So let's double check that. So first of all, note there's only 2 paths from A to C. Either we go there via B, which gives us a length of 2, or we go there via V1, V2, and V3, which gives us a length of 1, 2, 3, 4. Now the optimal path is clearly then to go there via B. So the optimal path has a length of 2. However, what's A star going to do? Our new algorithm that uses this heuristic, it's going to start in A, and it's going to check B and V1. For B, it's going to see that, okay, we can get there in 1, but then our heuristic says that to get from B to C will take us 1,000. So that's 1,001 to get there. That doesn't sound great. The alternative is going from A to V1, and now our heuristic says, well, you can get there instantly now from V1 to C. You can get there with 0 extra cost. So A star will say, okay, excellent, I'll go to you then, because you can get me there instantly. But now we get there, and turns out our heuristic was wrong, and all we can do is now go to V2. But again, according to our heuristic, from V2 we can get there instantly. So A star can choose 2 plus 0 or 1 plus 1,000. So it will again take this one. And then it will take this one. And then it will get in C with a length of 4. And C will be the closest one because B is still at 1,001. So it will say, okay, I found my path to C. I've gotten it out of the queue with a distance of 4. Can't beat that. So 4 over 2 gives us 2 as the answer to this question. But more importantly, this shows why A star can break when we have a wrong heuristic. So what does that mean? What kind of criteria should this heuristic fulfill? Well, there's 2 important things here. First of all, the heuristic must always underestimate the actual length. So just now, the actual length from B to C was 1, but our heuristic said it was 1,000. That will break it, right? So our heuristic must underestimate the actual length. That ensures that when we stop, because we've gotten it out of the queue, well, there is no shorter path to find here, because our heuristic was an underestimate, and the actual path leading here must always be at least as long. So there's no shorter way to get here. So that's one. Heuristics must underestimate actual length. What else? Well, if we have this cloud or this visited set of nodes, then our heuristic must be monotonic. What does that mean? It means that getting from a vertex U to a vertex T must always be, the heuristic from U to T must always be less than going from U to V, and then the heuristic from V to T. Right? So going via some other vertex must always be more, or must at least be equal or potentially more. It's basically a way of keeping our heuristic consistent, if you will. So including an extra vertex in our path will always result in the same or a larger distance. Do these properties of heuristics make sense? Any questions about them? I see someone tried to post a link in chat. If it's something important, try posting your message again without the link so that I can take a look. Okay, I see no questions popping up. If they do pop up in a bit, I can answer them then. All right. So heuristics must underestimate the length, and they must be monotonic consistent, right? Going via another vertex can never make our path smaller. Now then, these examples that I showed you, Euclidean distance, is that a good measure? Well, yes, assuming that the graph is in a Euclidean space, right? Then the Euclidean distance is a good heuristic. The Manhattan distance, again, well, yes, assuming that we are in a Manhattan space, so that we can only move at one axis at a time. If not, if I can also move diagonally, let's say, then this thing will overestimate distances and therefore ensure that our algorithm produces the wrong answer. So Manhattan distance is a good heuristic, provided that I can either move diagonally, horizontally, or vertically, but not both at the same time. What else? The difference in node ID. Well, hopefully it's clear now that that's a terrible idea. Because that doesn't mean that including another node will get us a smaller distance. It doesn't mean that we don't overestimate distances. It tells us nothing, essentially. Put them all to 0. Well, that's definitely underestimating them. Hey, but if I put them all to 0, then I've just created Dijkstra again. Now I told you can use any other constant. Is that true? Well, yes, provided that constant is smaller than the smallest edge in our graph. If it's not smaller than the smallest edge in our graph, then we could be overestimating distances again, and therefore things could break. But if I know the smallest edge in my graph has a weight of 5, I can safely put my heuristic to weight 4. The question is, why would you? If you do, well, you might as well put them all to 0, right? Okay. So some example heuristics we've seen. So now we've seen two algorithms. Dijkstra on the one hand, without this heuristic, and now Dijkstra plus a heuristic for A star. And the question now is, okay, which is better, right? Which should I use? I'll give you a second to read the comic first. So how do we compare these two things, these two shortest path algorithms? A star claims to be an improvement over Dijkstra, so does that mean I should always be using A star? Well, you've taken this course for 7 weeks now. You know my answers are hardly ever yes or no. My answers are usually, it depends. And of course, that's also the right answer here. So what are our options? Well, on the one hand, we have Dijkstra, which finds us the shortest path in v plus e log v time. It's an efficient algorithm, and it requires no further knowledge of any context. Just give me a graph. I don't care what it represents. It could represent the Dutch railway network. It could represent a set of jobs that you need to do with a certain time indicated on the edges. It could represent anything, and I'll find you the shortest path. Now that's great. I don't require any knowledge of this context, but it also means I cannot exploit this context. If I were to know, for example, that it is in a Euclidean space, well, then I could use A star to improve my performance. I could use a heuristic. And so that's great, because if I have a good heuristic, I can consider far fewer vertices and thus be done quicker. My asymptotic runtime will remain the same, but given a good heuristic, I will consider less vertices and therefore become faster. But that has a major downside. I need to have this contextual knowledge to produce a good heuristic. Now, I happen to like video games as well, and some of you might know the video game Factorio. It's a game in which you build a large factory. And in this factory, you can also have trains bringing resources from one place to another. And recently, the developers wrote a whole article about how they'd optimized the pathfinding of these trains, and they concluded by saying, well, what we did is we went from Dijkstra to A star we added a heuristic, which we can do because we know what our map looks like, how our physics work. And so we added A star with a heuristic, and our algorithm became twice as fast. And that's amazing, right? Twice as fast is, okay, it's only a constant improvement. So again, in terms of time complexity, no improvement. But in terms of actual runtime, it can make a huge difference. So A star, absolutely love it, but it requires you to have contextual knowledge. And without it, well, you can always fall back on Dijkstra, which will always do the job. All right. That means that after today, you have seen also topological orderings, this way of finding an ordering of vertices so that when it's a dependency graph, we find a way of doing all of the jobs while the dependencies are satisfied. And we've taken a look at shortest path algorithms, and we've seen two. We've seen Dijkstra repeatedly pick the closest one to your cloud, and we've seen A star repeatedly pick the closest one to your cloud, but keeping in mind that from that point we add, we still need to reach our target. And we have some estimate, some heuristic for that last distance. Tomorrow, as I mentioned before, will be a regular lecture. Well, as regular as we can be over Twitch, but okay. Where we talk about MSTs, or minimum spanning trees. And if time allows, we'll do one quick extra exercise, but I'm not sure if time will allow. On Thursday, we will have a regular tutorial. Next week, we talk about P versus NP, which I'm really looking forward to. And then 2 weeks from now, or sometime after that, I hope to let you know soon, we'll have 2 more exams. Before Friday, please make sure you check the feedback on your written exam. An email you will get soon about that. I'm going to look into it right now. After today, you can read a nice chapter of the book that is also about shortest path algorithms. And before Sunday, there will be a new set of homework exercises for you to work on. I've asked one of the TAs whether they can upload them to WebLab, and I hope today will have done so by tomorrow morning at the latest. Other than that, I will see you back tomorrow for a lecture about minimum spanning trees. If you have any questions before then, I'll stick around in chat for another couple of minutes to see if I can answer some of them. See you tomorrow.